Hi, I'll be talking about our work on cost control in display advertising, theory versus practice. This is a joint work we did at Zolando. Advertisers run marketing campaigns with budget and cost constraints. Here we consider cost per view. This is formulated as an optimization problem of the form maximize advertiser utility such that spend is less than or equal to budget B and cost per view is less than or equal to the target cost per view C view. From the optimization problem, an optimal bidding formula is derived. At every request, a bid is placed using the optimal bidding formula. Mu and lambda are the dual variables associated with the budget and cost constraints, respectively. After every n requests, the dual variables are updated based on the actual and the target spend and the actual and the target cost. The optimal bidding formula assumes that the values of mu and lambda are also optimal. This is possible in offline optimization where we have access to the entire dataset and the optimal values can be computed offline. However, in an online setting where data is coming in real time, first, the optimal values are not static, that is, they change with time. Second, it takes time to converge to the optimal. For cost constraint campaigns in particular, which are the most relevant here, the optimal lambda is 0 because budget is not an active constraint. The optimal mu is infinity and the optimal bid is C view. With the optimal bidding formula, it can be shown that bid on average is greater than or equal to C view. This is visualized in the figure on the right with C view equals 1. This means in case a campaign exceeds C view, there is no way to correct it. This makes the algorithm ineffective at cost control. What if we introduced a discounted target called CView dash, which is beta times CView, where beta is between 0 and 1? From before, we know that bid is greater than or equal to CView dash. This means bid may drop below CView if it is necessary to make any cost corrections. This is good. However, even after the CPV decreases to the original CView, mu continues to grow to infinity because the error in the online update is computed against CView dash and the bit keeps dropping towards CView dash. This is obviously suboptimal as it hurts the advertiser utility. We propose taking the best of both worlds. That is, modify the bidding formula as if there is a discounted CView dash, but do not modify the online update formula, meaning compute the error against CView as before. With this, we propose the new bidding formula where we introduce the beta term. On the right, we can see that bid may now drop below CView, which is 1. For beta equals 0, bid may drop all the way down to 0, while for beta equals 0.5, bid may drop to 0.5. We argue that this will result in a more effective cost control. In order to validate this, we first run some simulations on the synthetic data. Below, we show a scenario where cost is the active constraint and the budget is sufficiently high. We compare three different variants. First is max cap. Here we simply cap the bid at CView, which is 1. Second is cost control theoretical. This is the optimal bidding formula shown before. Third is cost control practical. This is the proposed change with beta equals 0. The simulation runs for a day and we visualize how lambda, mu, and CPV evolve through the day. Because budget is not an active constraint, we can see that lambda goes to 0 for all variants. Cost is the active constraint. Therefore, for cost control theoretical, we can see that mu is positive and in fact goes to infinity. And for cost control practical, the proposed solution, mu saturates and stays at some finite value. The CPV for max cap is slightly below 1 since this is a second price auction. The CPV for cost control theoretical is higher than CView and is never corrected. The CPV for the proposed algorithm saturates at CView and oscillates around that value. This shows that at least in the simulation, the proposed change can achieve an effective cost control. In the paper, we study more scenarios. If you are interested, I encourage you to refer the paper. Next, we test the algorithms on large scale real world data, that is, real world user requests and real world campaigns. The number of campaigns is in the order of thousands. As before, we compare the same three variants. In addition, we compare cost control practical with four different values of beta: 0. 0.8, 0. 0.5, 0. 0.2, and 0.0. As a measure of cost control, we report the number of campaigns with cost violations. Additionally, we report the uplift in the advertiser utility over max cap, which is treated as the baseline. For max cap, we can see that there are no campaigns with cost violations, which is expected. However, max cap also produces the lowest advertiser utility. Cost control theoretical violates cost constraint on roughly 8% of campaigns, but it has an uplift of 22% in advertiser utility over max cap. Cost control practical for all values of beta reduces the cost violations significantly. For beta equals 0.8 in particular, the cost violations are reduced by 50% while producing the same advertiser utility as cost control theoretical. Beta equals 0.5 produces even higher advertiser utility, but it leads to a slightly higher number of cost violations. In summary, we propose a new bidding formula with a beta parameter that reduces the cost violations by 50% while producing the same utility as the optimal bidding formula. The value of beta depends on how close the prices are to the bids, which is a property of the market itself. If there is a high competition in the market, then prices closely follow the winning bids. In this case, we need a lower beta to drop the bids and consequently the prices down and achieve a cost correction. On the other hand, if the competition in the market is low, then prices are much lower than winning bids anyway, and beta can be just below 1, say 0.9, to achieve a cost correction. Future work will explore other ways to achieve effective cost control and will attempt a theoretical justification for the proposed method. Thank you for your attention.